All right, let's go ahead and get started. Welcome back and happy Monday. Um, this week, we're starting to transition from looking at some of the ALU implementation specific details to the single cycle processor implementation. And I think this is a fun topic for this course. This is what we've been sort of building up to the entire time. And the truth is, for many of you who've been able to kind of keep up and have been coming to class reliably every Monday, Wednesday, Friday, a big chunk of this material should really be review. The labs have been building up to that point. Some of the little side design exercises we've been doing in class have been building up to that point. And there won't be a ton of really new things here, just sort of tying it all together. Before we get started, I wanted to bring up our schedule briefly here. So here's where we are in our week number 8, and the name of the topic is processor design, which isn't I don't know, single cycle processor is probably a better name for what this topic really is. That's lecture 7 that we're on now, and a quiz on Wednesday that may have to be at the very end of Wednesday because we really haven't covered a lot of that that's on that quiz that I've noticed yet. And then this week in lab, you're finishing and submitting project A and starting on project part B. And I think that's going to be a lot of fun. First off, you do have a lot of time to work on it. It isn't that many more lines of code than any other thing you've worked on so far this semester. It does require having a good design in mind, and really it requires being able to test and debug when things aren't working exactly the way you want them to. But you have plenty of time to work on that. So all of this should be somewhat in alignment for the next 5 or 6 weeks of this semester. That we're learning about things in class and you're doing things in the lab, and they're basically the same things. And that's my hope that that'll continue at least for the next 5 or so weeks. And then before you know it, the semester is really going to be over here. Um, so right, I called this topic processor design, and that's fine. It's really single cycle processor data path and control, and that is covered in pretty good detail in the beginnings of chapter 4 of the Patterson and Hennessy textbook. The main thing you have to kind of watch out for, and we've been running into this already this semester, is the book has the pretty reduced set of instructions, no pun intended, that they are showing you how to implement using their processor design. And that is a pretty small subset of the total number of MIPS instructions. And we in the lab also do not do all of the MIPS instructions, but we wind up doing more than what are just listed in the textbook. Now, having said that, every instruction is listed in the textbook. The green card has them all, that appendix in the back does describe them all. But the actual chapter 4 discussion of how to implement the instructions covers like 13 instructions, and we realize, I think, based on the ALU we've built, based on our understanding of some additional MIPS instructions, that without too much additional effort we can build a processor that supports quite a few more instructions. But when I say the material is 75% review, that really depends, and that's okay. So this material is either, as well as this lab, frankly, is either kind of catch-up material for many of you, where you're just kind of getting a feel for what is happening on a week-to-week basis, and then you have some time to kind of think about it now and put it all together. Or if you've really been following and really asking some deep questions of yourself and of the book and of me, then this is quite a bit of review, and that's fine. If this week is boring because you know all this, hey, stress out about other things in life. You don't have to stress about this course every single week during the semester. The main part that we'll call it your project part A design, where you tie everything together, or even just your lab 4 design. The only part we really don't have is the instruction fetch and decode parts of the processor. The rest of it you've really already built. And the question is now, how do you tie that all together? We've done a little bit of that in class, and let's just make sure we have a good feel exactly for what we are doing. With that caveat that the textbook gives very good advice for how to build this together, put this all together in that chapter 4 sections. You cannot just take that chapter 4 diagram and say I'm done, because we are supporting more instructions than the chapter 4 diagram. It's a pretty good starting point for us, and so you can certainly use it as a starting point when you have to build your own diagrams here. Our philosophy for designing the processor has been pretty consistent throughout the semester, where we separate between sort of the data path elements and the control elements of the processor, and also separating between, in terms of our circuitry, between the combinational logic and the sequential logic, things that have to store processor state, whether it be program counter or register files or in the data memory, and things that just operate based on the current state. That's your ALU. That's all your muxes and things of that nature. And we really just decompose our processor into those two different flavors of our logic. We start with a relatively simple breakdown. This is the so-called single cycle processor. By setting that as our design requirement as a restriction, that every instruction, from the simplest one to the most complicated one we support, is going to be executed in a single cycle. That makes a lot of things easy. At least it sets some clear direction for what has to happen in a given clock cycle. It also makes our performance analysis really easy, right? If we go back to the performance equation, if we are assuming that CPI equals 1, and that's what we can assume for this processor. That's what the term means, single cycle processor. That makes it pretty easy to go from instruction count to ultimate runtime, and we can do it just a direct kind of multiplication there, factor in our clock frequency, and we can analyze the performance of it. And it gives us a good starting point that when we start to relax that assumption and start to allow certain instructions to take potentially more than one cycle, we can have different performance profiles of our underlying implementation. So we start simple, then next week into the week after and so forth, we start to add more features to our implementation. So this is the textbook set of assembly instructions. If you were to look at project part B, and if you're still, of course, finishing project part A, you don't have to really look at it yet, but you have a couple days still, I guess. Um, it's very similar. So in terms of the type of instructions we're supporting, we're recognizing, for instance, that we are supporting more arithmetic and logical instructions. We've already built or are in the process of building um, a more complex ALU than what the textbook requires us to build. So we can support more instructions than the textbook has as its design. Likewise, although we haven't gotten there yet, we realize, or we've started to learn, how if you've put the logic in place to support a branch equal instruction, well, then supporting a branch not equal shouldn't be too much of an additional burden for you. Likewise, if you've already supported a shift left logical instruction, shift right logical shouldn't be too much of a burden. And so we've added a few additional instructions based on that sort of philosophy of, well, you already have 99% of what you need for that instruction. Let's add the next one. And then the other ones we add are ones that are very useful for running real programs. So the textbook doesn't have jump and link and jump register, but we've seen that that's a pretty important thing to be able to support, to be able to do function calls. And so we've added that, and we've been working on that and focusing on that as the semester has gone on. Um, it's not necessarily the case that those additional instructions we've added are any harder to design or debug for. Just in terms of the schematic where you're starting, that's where your efforts primarily have to be focused. Because for this class of whatever the number is of instructions we have here, the textbook diagram is sufficient, and you can just start and implement that and be done. But then you have to think about, for these additional instructions, how do I modify my diagram? You don't start from scratch, certainly, but you have to modify it and see what else is going to be needed for those instructions. The implementation strategy, excuse me, that I want you to work on for project part B, and we effectively split it into two sub phases for project part B, is to focus on all the I don't want to call them straightforward instructions first, but all the instructions that assume PC equals PC plus 4, the data flow, data path instructions first. So all of these categories here, I want you to focus on first and build circuitry that just supports PC equals PC plus 4. And then once that is completely working and tested thoroughly, then you start to think about, well, how do I add in the branches and the jumps? And it is for the best that you separate those two things. Um, the design aspects of those two are pretty orthogonal to each other. So we support all the logic to just go from the current instruction to the next instruction, whatever's next in our instruction memory. There's enough complexity here to give you a couple weeks of work with your team. And then we add in this as well. So for all the different control flow instructions, how do we support those? How do we test that? That's actually a more tricky thing to test. But having said all that, our generic implementation is the same as what we've been talking about this entire semester. That we have um, this sort of state machine update of our processor, which is using the program counter to keep track of what our current instruction is, doing an instruction fetch, looking at that instruction, figuring out what that instruction is supposed to be, that decode stage, and then executing that instruction. And that's still the case. That doesn't change with looking at this single cycle processor implementation. And one thing you will note, if you do look at chapter 4 of the book, and for some of the earlier diagrams we've been talking about this in the labs earlier in the semester, I've noticed it a bit that the textbook definitely tries to sort of bootstrap the design from conceptual to implementation details to further implementation details. So ideally, what I would want you to do, no one does this, but ideally, what I would want you to do would be to actually read 4.1 through 4.4 straight through. It's not that many pages. My hope is, again, the majority of that material would be review for you at this point in the semester now. But the trick when looking at any given page of chapter 4 in isolation is it'll have these either conceptual or partially implemented architectural figures for what the data path needs to look like. For example, this is directly a figure from the textbook early on in chapter 4, where they're talking about the two different types of functional units, the combinational logic units and the sequential logic units in our design. But I wouldn't want you, and the intention isn't for you to look at this diagram and say, well, this is my project part B design. This isn't. This is a much more conceptual view. We can kind of see, I think that that's the case when we see stuff like this happening in the diagram where, you have all those wires kind of just mashing into each other at the second input to the ALU. We already know from lab 4 and whatnot what that is implying by looking at this diagram here. It's meant to show conceptually something important. And each figure in chapter 4 is kind of attempting to build upon each other. So if you were to look at one figure, you'd want to look further along in chapter 4 at least. But ideally, you would just kind of read through it and see how they're kind of scaffolding the diagrams that they're building to show how to design this. Each figure has its purpose. Only one of those figures would be correctly labeled the single cycle processor implementation. And the remainder of it is just here's the steps along the way for how we get from concept to implementation. Um, there isn't that much of a takeaway from this slide, this figure in the textbook, other than that we're separating between those memory elements, those state elements in our processor, and those just data path logic elements. This concept I've mentioned very briefly, and it's not a very important one, but for our implementation, it makes our life a lot easier. A so-called Harvard model or split memory model for our data and instruction memories. That while we recognize that perhaps ultimately memory is just one physical thing located in my system, although there's various layers of it, but ultimately it's one sort of physical storage, DRAM or whatever it may be in my system. It's a lot easier to logically kind of lay out the processor, design for the processor, if we assume that there's sort of a physical separation between what's in our instruction memory and what's in our data memory. That is a little bit of an abstraction that makes our life easier. In terms of how we implement it in the class, we actually do physically keep them as separate memories. Ultimately, that doesn't quite work, right? Instructions are data. We've talked about that already. Data is data and instructions are also data. So all the things we need to do with data memory, we also technically need to do with instruction memory. But by separating the two, it does make our design a lot more straightforward and simple to work with, such that when we look at our instruction memory, for instance, we can think of this as just a read-only element now. That somewhere at some point, instructions got fetched or got, loaded into our instruction memory model, our module here for instruction memory. And then at runtime, all we're doing is just reading from that. So it's any other combinational element in our design. It's not a full memory that we have to worry about write enables and things of that nature. Whereas then the data memory is separate because based on whether it is a load word or a store word instruction, we have to potentially either read from the memory or write to that memory. One aside, I've noticed a lot still, and that's okay, that which one's the load and which one's the store is something that I think a lot of you are still forgetting. I almost want you to write it down on a piece of paper and stick it next to your monitor. Load is relative to the memory. We are loading from memory. Store, we are storing to the memory. You'll want to have that nailed down as you start to implement these instructions because you'll have really weird bugs if you occasionally forget which one is which. Not just assembly language bugs, but implementation bugs if you tend to get that occasionally backwards. And we've seen versions of this figure as well. And this is what I was mentioning, that, there's a lot of primary review here. So with our sequential logic, our typical execution is that we have some reading of our state elements. That is the program counter and potentially our registers in our design. So we're reading from those state elements. Then we have this, I tend to draw it as a cloud. The textbook just shows this nice clean oval, this sea of combinational logic that our signals are routing through. All of our muxes, our ALU, everything else that's happening in our design is in that oval in this figure here. And then for the end of that single cycle instructions execution, we're updating one, potentially multiple state elements on that clock edge. And here it's showing as a writing on the falling edge, but it doesn't really matter as long as we're consistent with if we take the rising edge versus the falling edge. The design is exactly the same either way here. But we have the things that get read at the beginning of the instruction. We have all the logic that is required, and then we update our state elements. Again, we update our program counter. We potentially update our register file, and we potentially update our data memory at the end of that cycle. And that does assume that there's some control signals for that writing. I think for the program counter for our current design, by and large, we can hardwire the write enable to 1, because generally for our single cycle implementation, if we have a current instruction, we'll have a next instruction. We'll go from PC to PC plus 4 at the very least. So we need to update that program counter. If it's a branch or if it's a jump, we have to update it to some other value, but we still have to update it every cycle. But that's where that global write enable for the register file becomes important. Some of you, I think, were already seeing this when we started on Lab 4, that not every instruction is going to write to the register file. So we need to have some control for that register file, because jump instruction, for instance, or branch instructions, they don't write anything to the register file. Store word instruction does not write anything to the register file. So for those instructions, our control signals we have to set accordingly, and to make sure that we only update the state elements that are relevant. I think we see this intuitively for the data memory. Yeah, there's only one class of instructions that writes to the data memory, so we need to make sure we have some mem-write control signal for our data memory, but we also need it for all of our state elements in our design. So those two things have to happen. If it's the rising edge, or if it's the edge of the clock, and if the appropriate write control signal is asserted for that particular element. So let's jump into the design. And again, as I mentioned, my hope is a lot of this is boring to you. I mean, boring probably isn't the right word I want to use. I hope most of this is just obvious review, and you just feel really validated in the efforts you've put in so far this semester. That's a much better way to phrase it. But if it's boring, so be it. They can't all be just super duper exciting. This part is the part we haven't done yet. We did a little bit, in terms of a pencil and paper. We haven't touched this at all for our implementation yet. But that first part, that instruction fetch, our first part of the implementation of a given instruction, is to read the instruction from the instruction memory. So our program counter, which is going to be a separate register that you are going to have to implement, and don't get upset about that or scared about that, right? It's just a separate register that you have to implement, and we already have a register, so we just have to instantiate another register in our design beyond the 32 that we already have. We are going to read from the program counter, connect that directly to a read address of another memory module that we're going to consider as our instruction memory. And then the output, the data read port of that instruction memory, is going to correspond to what our 32-bit instruction is going to be. And then as part of that basic fetch, decode, execute cycle, whether this happens, early on or later on, doesn't really matter. By the end of that instruction, we do need to make sure we've then updated the value of the program counter. So at that edge of the clock corresponding to the end of the current instruction, we want to make sure that the program counter's value has, at the very least, if nothing else has happened, +4 added to it and stored back as the next program counter. Certainly, this is where labeling your design becomes becomes pretty important. so that you can keep track of which signal is which. And labeling was always important, I believe, all semester, but I think especially important as you start to put the whole thing together. Otherwise, my recommendation is not to overthink the individual components. You already have an adder that you've built. The data flow adder is also perfectly fine for this purpose. We don't care at all about final carryout or overflow or anything of that nature for this PC plus 4 adder. Just instantiate that adder. In terms of the second input, the diagram is showing you, and I'm explicitly telling you, it's just 4. It's never something else. So you can actually just hardwire binary value 4 to that adder's second input, and you have an adder that isn't an add slash subtract unit like we've already built. It's hard coded just to be an adder. Whether or not that's the most efficient way to build it doesn't really matter. The synthesis tools can likely, as we've talked about, take care of a lot of the rest of the details. If it knows it's already an adder, it probably gets rid of the entirety of all that subtraction circuitry. If it knows that you never even look at the carry out signal, it gets rid of that carry out signal very likely when it actually synthesizes the design. But the beginning part of your project part B processor should basically just look like this. Instantiate a register, call it program counter. I'll wait for people to get to that point. We have to initialize it a little bit carefully for things to work properly. But we'll get to that point when we get there. Instantiate an adder with a +4 as an input. As long as this gets written on the edge of the clock cycle, you'll have this state machine, this part of this state machine effectively implemented. And you should be able to see in ModelSim a register that's counting, going from PC to PC +4 to +8 to +12, etc. Decoding instructions is also the thing we haven't done yet, although we've certainly talked a lot about it. I keep mentioning the spreadsheet over and over again. We'll now go into Canvas, and the spreadsheet is actually available for you to take a look at. I want you to use the spreadsheet template I provided just so it's easier for us to grade what other people have done. Um, it is just consistent. It makes life easier for the TAs. But again, we take as input to this module our actual instruction itself. That's just the 32 bits. And so far to this point in the semester, I think for the vast majority of you, we haven't had an instruction yet in our design. We've just had manually set control signals. And so there's been a lot of questions about, what ports do I need in my Lab 4 design, or what ports do I need in my Project Part A design? And you may have noticed I wasn't super engaged with those questions because it doesn't matter is the answer. Not now we're moving on to Project Part B, and there's really hardly any ports needed for this design. There's a clock, there's a reset, there's some output ports we put for testing and debugging purposes. But that instruction, starting now that we have an instruction memory, is entirely this internal thing, right? It's this internal signal, just label it instruction 32, whatever you want to label it, that we are then going to be peeling the various bit slices off of for our various purposes, right? That's where the RD, RS, and RT fields, that's where our 16-bit immediate is found. It's where our shift amount is found. Opcodes, function fields, that's where that's all found. It's all part of those 32 bits. And we don't know yet what type of instruction it is. We just have this 32-bit signal coming into this part of the design. The nice part is we're just grabbing wires. So it doesn't matter. Is it an R type or an I type? We don't know yet, don't care yet. We just grab the appropriate fields as if it were an R type, and as if it were an I type and a J type instruction. We're only going to use those fields once we realize what is what, once we know exactly which instruction is which. But we can grab those signals and we can just label those wires in our design. And this is another good example of a textbook diagram that is conceptual in nature and not entirely complete. So, because as the question is asking, this is showing a very specific set of fields coming off for read address 1, read address 2, and write address. We've already seen a little bit of earlier in the semester, and for Lab 4, I said, don't worry about this at all, because we didn't have an instruction. But we've already seen that depending on the instruction type, where that write address field gets encoded changes. So there will have to be additional muxes here, but we'll get there when we get there. What's new now for this is beyond the fact that these fields are not inputs into my design anymore, they're just internal signals in my design. What is new for this is this oval here referred to as the control unit. And I've said it enough times now, that is our spreadsheet. It is going to be a module that takes in our opcode and our function field in our instruction. And depending on the value of the opcode, it's going to set the various control signals in my design. And the reason I do believe the spreadsheet is such a nice way to encode this information and keep track of this information is first off, it's a file you can share amongst your project team. It's very easy to reason about and agree on what the right output should be. It is not basically a lookup table. It's exactly a lookup table, right? Where the address field into that lookup table is the opcode and optionally the function code. And the output of the lookup table is this bit string of control signals. If opcode equals all zeros, we know it's an R-type instruction. Consequently, reg write should be set to 1. But mem write should certainly be set to 0, right? We're definitely not writing to memory if it's a R-type instruction, and so forth for all of those fields we have. What I think is nice about this project, though, is the textbook describes a few of the control signals you're going to need. But because we're implementing more instructions, we'll certainly need more control signals than what the textbook provides. And everyone's project should look a little bit different for that reason. Certainly the names of your signals should look different. And if everyone has the same exact signal names, I'll be a little concerned about that. But it should look a little different. And so everyone's spreadsheet should look a little bit different. But in theory, and I hope in practice, you should just be able to go down row by row. Here are the 30 some odd, whatever it is, instructions we are supporting. Look in the green card or run them all in Mars real quick. Here's the opcodes for each of them. Here's the function fields, if needed, for each of them. Here's, for each column corresponding to a control signal, what that output should be for those control signals. And then implementing that is one big case statement in VHDL. And it should be pretty maybe a little bit lengthy because you do have a lot of named signals for those control signals in your design, but it should be a very straightforward implementation from a spreadsheet, almost kind of a copy paste into your VHDL file case statement. Case, if it's 00000, then here's my output bit vector. If it's instead this, here's my output bit vector. Just a big switch statement for our decode scheme that we have there. And in that stage also, it's called the instruction decode stage, but we're also going to be then just reading our registers. And I've mentioned this a couple times already, but we can read from those combinational elements in our design. The textbook's explanation of it is, we don't know yet what the instruction is, so we're working ahead by reading values from the register file. The way I like to think about it is there's no harm in reading from the register file at this stage. Even if it turns out to be an instruction that makes no use of the register file, of which there's only one, right? Our jump instruction doesn't use any registers at all. There was no harm in reading from the register files. We didn't change the processor state. Writing to the register file, we have to be very careful about. And with data memory, it really depends on your implementation. But for our implementation, there's no harm in reading from the data memory. We haven't changed any state of our processor by reading from the data memory. At least in our memories implementation, that is the case. And for the register file, it's certainly the case. There's no harm in reading from the register file. When we want to write to the register file, we have to be very careful. Only write to the register file if there's a good reason to do so, if the instruction requires it. But for reading from the register file, hey, let's just do it anyway. Let's take a look at those signals corresponding to our read address 1 and read address 2, and let's actually read those values out. Because as it turns out, and I think we've got this, almost all of our instructions, save for just the plain old jump instruction, are going to be reading from the register files and making use of some register file values. As we connect the execution stage, now at this point, it starts to depend on what type of an instruction it is. Again, if we think of these 5 phases of execution, from instruction fetch, decode, execute, memory stage, and then write back stage, those first 2 stages are basically the same, no matter what the instruction is doing. No matter what it is we fetch, no matter what it is we decode the instruction, and I'm telling you, we can read from the register files, and there's no harm in doing so. It's only in this 3rd stage that what we do really depends on what the instruction is. And this is where your spreadsheet becomes handy. This is where you also need to have a pretty thought out diagram for starting at this point. But the nice thing about it is you've done, 95% of this already, depending on how your project part A went, depending on how your lab 4 went as well. For others, I understand, it was a partial implementation. You have to kind of think about it some more, and you have some time to do so. But if you got 100% on lab number 4, you're in pretty good shape for this part. And even if you lost some point, the TAs could be a bit strict with some interpretations. If your diagram made sense, you're in pretty good shape for this part. And for the R format instructions, we see that as sort of a direct connection between the register file values that we're reading and read in the previous stage of execution of our single cycle instruction to the direct input ports of our ALU. So we have to figure out still what operation we're doing. And this is another place where everyone's implementation should look a little bit different. And the textbook will talk about a very specific ALU control scheme where 0, 0 means add and 1, 0 means subtract. But that's all pretty meaningless, right? That's a function of what order your inputs to your mux in your ALU happen to be. And there should be a lot of variety with regards to what you called those signals and how you maybe even ordered things in your design. But ultimately, there's some signal that has to be called. We've been calling it ALU op quite a bit, but ALU control, that has to be some signal that determines, even for our R-type instructions, the opcode was 0. We now have to look at that function field and figure out, okay, what are we actually doing inside my ALU? Everything else in the instruction is going to be exactly the same. The only difference is what signals are then being set for here. So for from our spreadsheet's perspective, if opcode equals 0, no matter what's in here, the remainder of the instruction, the remainder of our columns in our spreadsheet should be exactly the same. The only difference then is, well, what's my operation for my ALU? So testing, and somebody asked, but do we have to test both an XOR instruction and an AND instruction? My answer is, yeah, why not? It should be a really straightforward thing, right? Everything in the design is exactly the same. The only difference is what your ALU is doing. You built your ALU to support those operations in project part A. If you tested those and they work properly for project part A, incorporating that design into this single cycle processor should just be a matter of running the test and confirming that things do what they are supposed to be doing. And from our perspective so far, the textbook talks quite a bit about this, but it doesn't really matter, right? We've recognized already that our set less than instruction, one implementation strategy is just to treat it as another ALU operation, and that's how you were supposed to implement that for project part A. And we talked about that quite a bit last week, that it's a 0 or 1 that gets returned for our set less than operation. So from our perspective, although set less than seems intuitively a lot different than like an add or an or operation, it's exactly the same. It's just a different ALU control that tells it to take the less result versus any other result. And we're writing that back to the register file like it was any other type of R-type instruction as it is. As we move on to the immediate type instructions, certainly for Lab 4, we've started to be able to implement those. There are some questions about, is something sign extended versus 0 extended? And I've been telling people, and I think it's still correct to say, well, look at the green card. The green card is correct. But I get you that the green card is really opaque and hard to read. Definitely, though, my answer for people asking this question now, for XOR immediate, is the immediate sign extended or 0 extended? I'm glad you asked that on Discord. I'm probably not going to answer it because you should have the tools to answer that yourself now. Load it into Mars, test a value. By the time it takes me to read your question and type up a result, you can get the result yourself for that question because you're gonna have to do a lot of that. If you think there's an ambiguity in the textbook or on the green card about any of these micro implementation details or ISA details, our measure of correctness is whether the results of your design matches what Mars produces. And I'll be making a separate video as sort of the pre-lab video for Project Part B, where I tell you about the testing framework and kind of show off the testing framework, which is doing exactly that. It runs Mars for a piece of code. It collects all the register write and memory write operations that happen. Then it runs your simulation and it just compares the result. So there's no ambiguity there. What Mars runs is correct for our version of correct. And Should your instruction do something? The answer is, what does Mars do? And if it does that, then it's correct. And if it doesn't do that, then it's in fact incorrect. So we talked about the load store instructions as just a special case of the immediate type instructions where we're encoding some information in that immediate 16-bit field here. For the loads and stores, it's that address offset, right? We still have to read from the register file for these load and store instructions to read our base address, and then we're going to add that base address to the sign extended 16-bit immediate to get our 32-bit address for our memory. Part of the issue with that is why that was a little bit tricky is so many of our examples are using 0 for our offsets for loads and stores, or like 4 or something like that. So you're not really seeing all of the usefulness of that instruction. And likewise, we're implementing with a relatively small memory for practical reasons. So you're not seeing the whole 32-bit address space there as well. But the same operation is the same, whether it's an offset of 0 or an offset of 64K. It's going to give you the same exact operations, and your math in your processor should be doing the same exact thing there. If you built this for Lab 4, you're already done. The only difference now is instead of this immediate being an input to your processor, it's now just grabbed directly from the instruction field. The logic doesn't have to change at all from what you've already done for Lab 4 going into Project Part A. And so the design kind of looks like this. Again, this is another intermediate diagram that the textbook will show you, and you have to keep reading through chapter 4 to get to the final correct diagram. But conceptually, it's not showing the instruction fetch side of things, but we've done all the instruction fetch and decode, and now we're starting to see what are some of the control signals we need in our design, right? We need a field for our register write. For most instructions, that's a 1 because most instructions write to the register file, but not for all of our instructions. We need some field for our ALU op, right? Our ALU control. What operation should my ALU be doing? This is why I did ask you to kind of integrate your 32-bit conventional ripple carry ALU with your shifter and just make it a big box called ALU. Because then you can just have a single control signal driving that versus having to keep track of a whole separate set of control signals with different names. Your ALU control is going to be more bits wide than the textbook one. Well, they don't talk about shifts at all in the textbook, and we've added that. So you have one bigger box called ALU that you've built for Project Part A or are in the process of building, and then you're just going to have a wider control signal for it. In doing so, it makes it look as close to the textbook as possible as you build the rest of this design out. And then we have potentially control signals for our data memory as well. I think we should agree that memwrite is necessary for us. We only want to write to the memory file, to the data memory, when it's an instruction that requires it. Only for store instructions should we ever write to the memory for data memory. The textbook talks about a memread signal. Again, for our data memory implementation, just in the labs, it's not really necessary. There's no harm in having one, but there's just also no harm in reading from the data memory every single instruction, even if we're not actually using that value here. So this diagram is showing the data flowing through the system if you were only supporting those load and store operations. Read from the base address as a register, read from our immediate field for our constant offset, do an add, so it's like an add immediate operation. That result is our data memory address, whether it's a read or load or a store instruction. We still use that second read port from the register file. If it were to be a store word instruction, that would be the actual value we would store back to memory. And then finally, if it happened to be a load word instruction, it's that read data port of the memory would be what we could then connect back to the write port of our register file. Again, if you looked at that diagram just in isolation from the rest, your design would be wrong, right? This is the part of the data path that supports only load and store. We have to then sort of merge that, which I know you've already done to some extent, with the data path to support the other instructions and kind of connect them all together using the muxes to decide which of these paths we're taking for any particular instruction, right? We know a little bit of this, but certainly, for this write data port, I think we should know based on our Lab 4 design that this path, this red wire here, is only valid for load word. And if it were just a regular R-type instruction, it's in fact this signal that we'd want to connect back to our write data. We have two potential signals that need to connect to write data, depending on which instruction. That's our use case for the mux, right? That's why this is the add the mux course, because if it's an R-type instruction, connect this signal to write data. To write data. Else, if it's a load instruction, connect this signal to write data. Two possibilities, one signal they have to connect to for that port. That's our use case for the mux, right? It's one or the other. Then we have to have some control signal in your spreadsheet that says, yes, based on the opcode, I need either this value or the other. But effectively, we're implementing all the instructions at once, in a sense, and we're just selecting the output signals from the instructions that we are actually trying to execute at any given time. Branch, the main complexity I think with branch is interpreting what the green card is saying for what branch is doing. It is also an I-type instruction, which in the 16-bit address offset, we're encoding a number of instructions away that we are hoping to branch. And if you look at the green card, it says take PC plus 4 plus this encoded branch target offset, and if the branch is to be taken, make that our new PC. And because this is encoding an instruction offset, not just a byte offset, we do a kind of free shift left logical by 2. And I know that that was a little confusing when we had the quiz question about that, but we do that because we never want to ever branch into the middle of an instruction. So you would never want to have a branch in which the end result was a value of 3 or 7, because each instruction is 4 bytes. Our potential relevant PC values would always be a multiple of 4 for that reason. And so consequently, we'd be wasting a couple bits of that address offset if they were always zeros and we had to encode those 2 zeros. Instead, let's assume those 2 zeros are implied, and that for that 16-bit field, that gives us a range of 16 bits of instructions we can branch to versus a 16-bit range of bytes we can branch to. And logically, then it looks like something of a shift left logical by 2 to turn that into our byte addressable program counter value. So we were doing a sign extension. You know, whether this is going to be a separate component or just a little piece of data flow logic is kind of up to you. We would take that 16-bit encoding and concatenate 2 zeros at the end of it, effectively, to turn it into our byte offset. And then based on the specification for MIPS, we would actually take the PC plus 4 value and add it to that branch encoded offset to get what would be referred to as the branch target address. That signal could also be labeled as, if the branch were to be taken, here's what we would want the next program counter to be. That's a bit wordy, so we just call it the branch target address. That is where we should be branching to if the branch instruction, if it were a branch instruction, and if it were a branch instruction that we want to actually take. That is what the next program counter would be. Just like you already would have taken in a traditional adder that you already built, just use the data flow adder. For a plus 4 adder, you are also going to have separate from your main ALU, and this is to be a separate instantiation, a separate structural mapping in your design, now basically a third ALU, or at least a second additional adder, just to calculate the branch target address. It takes the result of your PC plus 4 value, adds it to that shift left 2 version of our encoded 16-bit value. So PC plus 4 gets executed, but it's a little misleading, this figure. So let's go to the completed version of the figure for the branch, because this path is not correct now. Now that we have to also support, the branch instructions as well as the traditional PC equals PC plus 1, PC equals PC plus 4. We can't have that path anymore. That path is now incorrect. But we do have at least basic logic. Someone's asking a interesting question about, can we implement this via sort of carry logic into our adder? You absolutely can. Which one is easier to debug is kind of up to you. right? Adding a constant though versus using a carry input it doesn't really matter. The logic tends to get optimized away anyway, but that would also potentially work for your purposes. Um, Jump is a little bit different from our branches in that for a jump, we're no longer doing a PC relative calculation anymore. We're basically just replacing the program counter with this new value for what the program counter should be. We can't replace the entire program counter only because we just don't have enough bits to encode that in this instruction. If we were to compare jump, which the textbook describes, to jump register, which the textbook doesn't describe, then in the jump register, we'd be replacing the entirety of the program counter with this register value. But for a regular jump, we have those 26 bits available to us because we still have the 6 bits for the opcode. We replace those 26 bits. Let's rephrase that properly. We replace the relevant bits in our program counter with that 26-bit field we have in our encoded instruction directly. It's doing a shift left logical 2 for this implementation for the same exact reason we're doing it for a branch. Just a more efficient way of encoding our jump target for the same reason. Those 2 least significant bits of your program counter will never, for MIPS, be anything other than 00. So why waste an encoding of 2 bits by encoding that directly? They're inferred. They're implied by the encoding here that we can instead now for those 26 bits we can kind of tack on our 2 zeros at the end of it, and now we have 28 bits that we can use to overwrite the program counter value directly itself. And unlike in the branch, where we still have to figure out whether the branch should be taken or not, for our jump, it's always taken. It's not a conditional thing. It's an unconditional branch in this case. We're always going to take it here. So that was a lot of review. As you're starting to design your data path, this slide is probably the most important part I want you to recall, or this and the next one, I guess. That you have all the various data path elements, and the nice thing is you've built them all. You probably don't need to make another functional unit this entire semester. It's built, it's done. You may have to revise yours because your tests are recognizing that some things didn't work as well as maybe you claimed it did, earlier in the semester. But you've created all the data path elements. You have to add the control logic and design the control path for it. But in our single cycle design, because we're not able to reuse any of those data path elements, we have just, for example, the one write data port on our register file that gets written to once per cycle for a given instruction. We're then going to need to take a look at those data path elements that need to be shared between different types of instructions and add those muxes with control lines to do that selection between those values. So as you draw your diagram, and you can start with the textbook diagram, and it's recommended to start with that or redesign your textbook diagram. If you made a really good project or part A or lab 4 diagram, you can certainly start with that. Every time you see this in your diagram, where it's 2 wires kind of just mushed together, well, you now know, I think, that's never going to work in your VHDL, right? You're going to have multiple drivers on that line, and it's just going to be all X's in your design. That's when you need to think about what control logic is needed in your design. The textbook covers maybe 4 of the 15 examples you're going to need in your design ultimately for muxes you have to insert to support these different classes of instructions. This one, this one we already did, right? We have our second input to our ALU, and depending on if it's an R type versus an I type, we either take the register value, or we take the sign extended immediate. That needs to be a mux. Textbook calls that ALU source. It's not a very good name for a mux. We have a lot of ALU sources in our design. I don't know. Call it ALU source B reg or immediate or something like that. The longer you make those signal names, the more likely as you look at your spreadsheet, it'll make sense to you very quickly what the value of that signal name should be for a given instruction. Likewise, for our register write port on our register file, we have 2 potential inputs coming into it. Either it's the ALU output that is our value to be written back to the register file, or for a load word instruction, it's our read data port of the load instruction that gets written back to the register file. That requires a mux. two signals kind of smashing together to one particular port in your design, it's one or the other. And that's that mem to reg signal. And that's an okay name. Um, Load word output to register file, or load word or ALU output to register file. Make it really descriptive, and then there's no ambiguity with what that is doing. Every time you have that scenario in which there's two potential inputs to a signal and you have to select between them, that's when you'll need your mux. As we're kind of finishing up for here today, and we'll have to continue on this on Wednesday before we have our quiz on Wednesday. Yeah, there's a lot of stuff that's still not shown exactly entirely in this diagram, right? And that's kind of the risk, arguably, that the textbook is showing all these staging of diagrams to get to close to the quote unquote final one, and each one is intending to show you a point. This diagram's purpose is to show you that you need muxes in your design. Okay, that's obvious to us, but that's what this diagram is trying to show you. It's not trying to show you the entire design here. The entire design is going to have all those stages. It's going to have instruction fetch, additional control logic for muxing what our next PC should be. It's going to have the actual control logic drawn somewhere around here that takes the opcode and generates all these signals. And then it's going to have the remainder of those data path elements to actually execute those instructions. Let's leave things here for today. Um, a lot of this topic, as I said, is review. But it would be very helpful to look at chapter 4. Actually, take a read through 4.1 to 4.4, get the textbook version of what we're doing, because then the main questions that are kind of the interesting ones for us this semester are: what are we doing that's beyond the textbook? How do we deal with these additional instructions that aren't there in the textbook? And those can be kind of fun to discuss, because you'll see that you can use your creativity there to some extent, and people can have different implementations for the same general concepts. Let's leave things here for today. We'll have a quiz probably near the end of Wednesday, based on how things are doing. Again, these are just attendance quizzes. You get credit for showing up, and that's all that matters for those quizzes. But otherwise, as we transition to Project Part B, good luck, and I'm looking forward to helping you, with your designs as you go, and I hope you have a lot of success. Thanks.